Okay, we finished part 2 by talking about the components of our galaxy. We started out with the disk component because we live in a spiral galaxy. And the reason it's called a spiral galaxy is because the disk has kind of a pinwheel shape. Now, we don't know this directly for our galaxy because, of course, we don't have a view of our galaxy from above or below. We are embedded within it, and it's impossible to get above or below. We would have to travel for millions and millions of years on a typical spaceship to get there. But we do see other galaxies that look a lot like our own. And the spiral arms have been a mystery for many years because they're not actually a connected structure. Because the galaxy has somewhat a differential rotation, so parts on the inside rotate a little bit slower than parts around here, and then they rotate about the same speed. But if all these things were connected, the galaxy's arms would wind up very quickly, and we wouldn't see the spiral patterns. So we think that the spiral patterns are more like waves, density waves, almost like sound waves, or if you could picture waves in water. Water waves look like a connected thing, but in fact they move along, and the water molecules that are bunched up by the wave are different than they were 30 seconds ago when it was farther out at sea. So we think that these waves, these disturbance waves, move through the galaxy and bunch up material, and they induce star formation. You'll see in this picture of a very, very pretty spiral galaxy that the arms look blue because there's a lot of star formation going on, and the hot blue stars just don't last long enough to ever wander away from the place that they were born. Also, you see a lot of these pink flecks in here. Those pink flecks are H2 regions, or emission nebulas. These are stellar birthplaces, clouds of ionized hydrogen gas, and as well as dust. And in between, there's plenty of other stuff too. There's lots of stars in between the arms, except they are fairly dim stars, so they're not the big show-offs of the galaxy. And so the spiral arms consist of these long patterns of bright young stars, clusters, gas, and dust clouds. They're ripples of compression that move through the disk. Because of this compression, it bunches up material, and it helps induce star formation. You get stars, you get emission nebula, H2 regions, and you get a lot of bright O and B stars. They are very good tracers of the spiral arms. By tracers, we mean things that trace out where those compression waves are. Since they're short-lived, very luminous, they're very, very bright, and they just don't live very long. By the time the density wave has moved on, those stars have pretty much reached the end of their lives. Okay, the spherical component consists of the halo. Now again, this is obviously not a picture of our Milky Way, but it's a picture of a galaxy that is also a spiral galaxy. This one is seen edge-on, not face-on like the previous one. And it's very, very telling. You see the disk of this galaxy, and notice how dusty this disk is. It's opaque right here. You can't see through the thick dust in the disk. Again, this is why we can only see maybe 10% of the volume of our galaxy, because we are stuck in it, and we are embedded within the spiral arms where there's a lot of dust. And so, with visible light anyway, we can't see to the galactic center or to the other side of the galaxy. But I wanted to show you this part here. Bring your attention to this. This kind of faint glow here is the halo of the galaxy. There's little fuzzy bits here. These little fuzzy bits are the globular clusters that are orbiting around this galaxy, very much like our globular clusters orbit around the Milky Way. And you see the galactic bulge. Okay, so the halo consists of these scattered stars. They tend to be, instead of the disk that orbits around in a nice regular way around the center of the galaxy, the stars and clusters in the halo are more like bees swarming around a beehive. They have very randomly oriented orbits. They go around at funny angles, and they dive through the disk and back out again. Most are made of mainly very old, cool, lower mass stars and red giants. There's about 100 or so globular clusters, give or take a few. Again, these globular clusters, and here's a picture with 2 clusters in them, very close to the galactic bulge. They tend to be anywhere between 50,000 to 1 million stars. They tend to average about 75 light years in diameter, and they are highly concentrated with stars at the very center. They're almost like miniature galaxies. And they are the oldest structures we know of in the universe. They're between 10 to 13 billion years old. Now, we're pretty darn sure that our universe is a little bit less than 14 billion years old currently. So that means that these are some of the first things that seem to have formed in our universe. The nuclear bulge is kind of a cross between the disk and the halo in composition. It mainly has old red stars, but there is a lot of activity going on at the very center. Stellar populations. Okay, this is fairly important. It turns out there are two distinct populations of stars. This was discovered back during World War II, actually, back when there were blackouts in the Southern California region. An astronomer named Walter Baade used the unusually dark skies to take spectra of many, many stars. And what he found was that there were stars that had very, very low percentages of heavy elements. And since these were the first stars that he discovered, he called them population 1 stars. Ironically, these are actually these are the ones with some heavy elements. We call these heavy elements metals. Okay, the Sun, for example, is a population 1 star. It contains between 1.5 to 3% heavy elements. Now, an astronomer will call anything that's heavier than helium a metal. It's kind of a silly historical thing, but basically, to an astronomer, oxygen is a metal, calcium is a metal, nitrogen is a metal. It's not really a metal, but that's that's just the language. Every science has their terminology, and astronomers have terminology that's a little bit stranger than many. Basically, as we already mentioned in a previous mini lecture, these heavy elements didn't exist in the early universe. The universe initially, when it was created, was made of primarily hydrogen and helium. About 75% hydrogen by mass and about 25% helium. Where did these heavy metals come from? They came from the dust of exploded stars. They came from supernova explosions. And so, basically, we know that population 1 stars are actually not the first generation stars. They are second, third, and fourth generation stars. They're basically made from the partially anyway, from the recycled gas and dust of exploded first generation stars. So when supernovas happen, they scatter their enriched elements throughout the universe, throughout the galaxy, and then they mix together and make molecular clouds, along with some of the hydrogen that's still primordial, and helium, and they then condense into new stars, which are contaminated, if you want to call it contaminated with heavier elements or metals. Some of those heavier elements probably get left over and form planets. We now know that there are planets around many, many, many stars, perhaps most stars in our galaxy. And these population 1 stars are primarily found in the disk of our galaxy. Now, again, sort of numbering them backwards, Baade found population 2 stars, because those were the second stars he actually found. These are actually first generation stars. They're made almost entirely of hydrogen and helium. They have less than 1% of heavy elements, and they are found in the halo and in the globular clusters. So, two very distinct populations of stars. The first generation stars, population 2, are found in the outer regions of our galaxy, and population 1 stars, made from recycled elements, are found in the disk of our galaxy. Now, how do we map the spiral arms of our galaxy and others? Well, like I said, it's very difficult to see beyond a certain point in our galaxy. We can only see about 10% using visible light, and we don't have very good perspectives because we're stuck inside the galaxy. However, long wavelength radio waves can penetrate the galactic dust. Fortunately for us, besides hot bright stars, there's another really good tracer of spiral arms, and that happens to be cold neutral hydrogen clouds. Cold neutral hydrogen clouds naturally emit radio waves. This is kind of a strange thing. We're going to talk about how this happens in a minute. 21 centimeter radio waves are emitted by these clouds. It has a very, very distinctive wavelength too, which helps us because we can use the Doppler shift to figure out whether the clouds are coming towards us or going away, and that helps us map out the structure of the galaxy. Okay, so here again is that picture of the really beautiful grand design spiral galaxy that we saw before. This is using a visible camera. It turns out that these long spiral arms, in addition to having hot bright stars and bright emission nebula, also have places where there's cool hydrogen gas. Cool hydrogen gas, we're used to things that are hot giving off light and radiation, but what about things that are cool? Well, it turns out we can make a map of the same galaxy and see where the blobs of cool hydrogen are. The blobs of cool hydrogen give off this 21 centimeter radiation because hydrogen is a simple atom, and the electron that circles the proton in hydrogen, they both have a property called spin. You can sort of imagine it like a spinning top, but that's not really what it is. But just use your imagination. Think that they're little tiny spinning tops. It turns out that the hydrogen atom's ground level, you remember when we talked about ground level of an atom is the lowest energy level. Well, it turns out that the hydrogen atom's ground level is slightly split. Okay, when the spins are parallel, when the spin of the imaginary little top of the proton and the electron are parallel to each other, and they're both spinning, say, counterclockwise, like in this diagram here, they have a slightly higher energy configuration than when the spins are opposite. Say when the proton is up and the spin of the electron points down. When that's the case, it has a slightly lower energy. Well, every now and then, a hydrogen atom that's stuck in this configuration, the electron will flip. And when the electron flips, it loses a tiny bit of energy and emits a photon, a radio photon, with a wavelength of 21 centimeters. And this is the wonderful little clue that nature gives us that happens when to let us be able to see the hydrogen gas, even though it's extremely cold. And we can use this then to map the spiral arms, because the spiral arms have plenty of this cold hydrogen gas. It only happens once every 10 million years per atom, but there's so many zillions and zillions of atoms out there that it's like a constant stream of stuff coming out. Okay, the nucleus of our galaxy turns out to be a very energetic and busy place. You can't see it with visible wavelengths, but radio, infrared, X-rays, gamma rays observations can show you things near the center of our galaxy. And we see lots and lots of remnants of activity going on here. At the very center is a powerful radio source. In fact, it was the first astronomical radio source found besides the Sun, called Sagittarius A. It's the galactic center. It's only 10 AUs in size. To give you an idea, 10 AUs is about the diameter of the orbit of Jupiter around our Sun. Now, you might say, well, that's a long way. It's like 2 billion miles in diameter. Well, yes, or about 1 billion miles in diameter, sorry. Yes, that's a lot, but compared to the size of our galaxy, that's nothing. Infrared observations that can penetrate the dust show that the central parsec of the nucleus is crowded with over 1 million stars. So there's lots and lots of stars at the very center. And it turns out that these stars are moving around, at least in the very center, are moving around very, very fast, which suggests something very, very gravitationally strong at the center. But we will have to wait until we'll kind of leave that as a cliffhanger for you, and we'll talk about that in part 4.